Hello, I will be presenting, I will have a presentation about FastText and its vector norms and out-of-vocabulary words. I will visualize vector norms versus their term frequency or count. Then I will show that in certain way there is a similarity between FastText norm versus term frequency to word-to-vec norm versus term frequency. And I will also provide rather weak evidence, but some indication of the fact that the norm is correlated to context specificity, and also that not averaging over n-gram count can be a useful indicator, for example, for detecting non-English words. So I'm Vaclav Kosar, I study physics, now I develop software, I dabble a little bit in machine learning. Currently I work for a time-limited startup. They do analytics of internal communications and analytics. The communications, for example, calendars, Slack, and so on, to optimize communication within the company. So first, I will start with short embedding intro. So words can be represented by vectors. Usually we use dimensions between 100 to 300. The representations can be derived statistically, but usually today are trained. For example, a very common, very popular model is can be seen on the right, where from the words around certain vector we can predict the word itself. And the model is very simple. We just do sum of the vectors and then dot product with the whole dictionary and find the word. Usually the vector norms are actually not used, but you can get sort of a feel of what they mean by the fact that there is this dot product at the end. So the bigger norm, the more probable of that the word will be selected or detected. So it's some sort of you can get a feel that there could be some sort of specificity about the norm. So why we use these representations? Well, because they are useful, they are easily used for downstream tasks, and they also can be used just by themselves. For example, there's this cosine similarity, which is basically the angle between the two vectors. Vector norm is the length of the vector, but the norms are usually not used. So when I try to look at the interpretations of the norms, I actually found that it's hard to find any research, but there is this one paper. It's for word-to-vec norms from Shekel in 2015. It's called Measuring Word Significance Using Distributed Representations of Words. By word significance, they mean the context distinctiveness of the word, how well the word predicts the context, the document or sentence. And of course, they mentioned that there's this document term frequency, which can be used with the global or corpus document frequency to basically do the same thing. That's called TF-IDF. But they claim there that the word-to-vec norms are actually correlated to the word significance as well when they trained them on a corpus and within certain frequency band of the word. So for example, they took this corpus about quantum mechanics, and within certain frequency bands they found three words: inflation, as in space inflation, sitter, as in de-sitter, and holes, as in black holes. And they claim in the paper that that's because these words are very indicative of the few articles that were about general relativity in the corpus, and that's why the word vector length width together with term frequency can be useful. They also do this plot for their trained word-to-vec, and you can see with the increasing frequency, the norms go down, but with but at the other end as well. So there's this interesting shape, and I think that can be expected that the words with very, very low occurrence in the data set don't have opportunity to actually increase their norm significantly, but there's some middle ground there in their rather low frequencies, which take the highest norms. So how the FastText works? So the FastText is another word representation model. What they do in contrast to word-to-vec is that they don't embed just the word themselves, but they also look at the subsequences within the words themselves, and they do representations for them as well. And they do this for each word. So if they have this word in a vocabulary, they take the whole word vector, and then they add sum of all the n-grams within the word. And then they divide by the total count of vectors. So that's basically how FastText works. Why to do this? It's because they get higher accuracy, and as well, if you have words which are not in the vocabulary, you can still use the subsequences of the words, usually in the words, to create still some vectors, still represented somehow into this 100-dimensional space, which is not possible with word-to-vec, for example. However, there's this asymmetry, right? So, if I think I can, I don't think I can show that. But you can see in the equation that there are two parts. That there's this whole word, and then there's this sum of the n-grams. So, if you don't have the word in the dictionary, you have only the right side of the plus, and that creates this asymmetry. So later I use both these parts to create different norms and to study them, plot them, and do these toy experiments. I also collected 10,000 most common words in English to contrast them with the FastText vocabulary, which is in the standard pre-trained model. FastText has around 2 million words in vocabulary, but actually most of them are, well, many of them are these artifacts, maybe some concatenated words treated as single word, and so on. So this is useful to visualize where the normal words lie. So if we do the plot and we use just the standard FastText vectors, then we get the plot over there. On the vertical axis, there's a length of the vector or the norm, and on the horizontal axis, there's the frequency of the word, how they occur during training, or they count. There's this interesting clustering, there are 4 clusters of the common words. We can see those yellow points which represent them, and I'm not sure what exactly those clusters correspond to. Maybe it would be interesting to find out. Disadvantage of this is that the scatter plot was a little bit too scattered. So later, if you use different approach, you may get something more useful. So the second plot is where I display vectors where I use no n-grams. So I just use the whole word vectors. And you can see that the shape of the plot is very similar to the one forward to vec that was presented in this 2015 paper. And 10,000 most common words are sort of in rather narrow band. And what we can also see from few examples on the screen is that there is another hint of this norm is word significance within frequency band. And that's, when you look at the green point, that's drown, which is rather a common word, maybe capitalized, but still. Then the second point higher above that, the red one, is some word alpine, which I don't know what it means, so it seems very specific. And then there's this number tel, which is concatenation of two words. So it's probably very specific, but it's not a word. Yes. And the third plot, first scatter plot that we'll present is this other approach, where I, instead of using only whole word vectors, I use only the n-grams, but with a slight twist that I don't divide by the n-gram count. And when I do this, I see this very narrow band of the common words. So you can see there's this horizontal yellow line, basically, where all the common words have their vector norm almost the same. And I use this later in an experiment. So how to show that there is really this relationship between vector norm and word significance or word specificity. So there are actually there are these two. You can call two words. They relate to each other when one can be hypernym and one can be hyponym of each other. So, for example, month is hypernym of January. And that means that the January is sort of like a subclass or instance of a month. And similar, it's for color. So I have pairs color red, color black. And the thesis is that the more specific words should have higher vector norms, at least within some frequency bin. And actually, when I took all the examples disregarding the frequency completely, when I looked at the norm, at the vectors where I used no n-grams, I used only the whole words, then this norm was actually predicting with accuracy of 77% which one is which one is more specific and which one is not. It's not, it doesn't seem to be perfect measure. Maybe if I had more data, maybe I think there's this data set WordNet, and if I really had both pairs always at similar frequency, I could actually compare them and maybe I would get better results. But even like this, there seems to be indication that there is this relation. So what's other potential use of the norms? So they seem to really carry some information. So we can use them as well for detecting common English words. So if all the common English words are located around this one line on the horizontal line with very similar norm, then if you look at the histograms, we could take some Bayesian approach and try to predict which word is English, which is not. And I did this simple experiment where I took 3,000 random pairs and concatenated the words, generated all possible splits, and just looking at their norms, I was able to predict with low accuracy of 47%, but it's interesting that you can actually do this with something that's not considered usually useful. So to conclude, I did these visualize these FastText vector norms, showed you some nice scatter plots, and norms relative to frequency. There was this interesting clustering in standard norm. No n-gram norm was shaped similarly to word-to-vec, as could be guessed. And there's this weak evidence of word significance somehow to be related to the norm. And also not averaging over n-gram count. And in general, not averaging over words just which would be just anonymized, seems to be a useful thing to do. Code is over here at GitHub, and I have a blog at here, vaclavkosar.com. So if you have any questions, that would be the conclusion. Yes?
Do I understand it correctly that the norm might be of use in these cases? Because it is somehow, basically not somehow, it is directly related to the structure of the space itself, right? So the way you define your vectors, the metric of the space where these vectors are defined.
Yeah, that's a
norm. It's related with the norms, right?
Yes, definitely. That's very common metric in the space, but actually usually we use this cosine similarity, or at least in the application I've seen. So it's not. You're right. Or what is other?
Just to understand what is behind this.
Yeah. Yes. Any other question? Okay, so I think that's all.